Fiona Bose. Welcome to my channel, Learning Builds Life, and today we are going to talk about classification of bones. But today we will see structural classification. Classification. But this is not same as the classification of bones according to shape. That was different. Like we had long bones, the short bones, the irregular ones, the flat ones, pneumatic and accessory ones. As I said, it was mistaken to be fractures in medical legal practice. It's not that. Structural classification, we will see how we view a bone macroscopically and microscopically. Today, our discussion is how we see a bone macroscopically. Macroscopically means means that the bone we can see it like from far away or in a larger view, and microscopically is the structures which we see under any microscope type or something like that. It's about the tissues in detail, and here we are just having a rough idea of what the bone is from our naked view, from the naked eye. So let's begin. First, our topic is about the diaphysis or the shaft. Diaphysis or shaft. The diaphysis or shaft is like a hard substance. It's really hard. Personifies ivory, like ivory. But it's very porous. Porous means it consists of a lot of pores and like holes in it, but it's porous, but it's really hard, like ivory. And most of this, like the main strength of this diaphysis or shaft is in the cortex of the bone, which is the central part, like the central part of the bone. That is about the diaphysis or shaft. Not much to talk about, but now we will move to the cancellous bone or the epiphyses. Or cancellous bone, or we can also call it trabecular bone, and I'll tell why. It can be called trabecular bone because it's like an open structure. Not open structure. It's like it's openly formed, and it has again like a lot of pores. And trabeculate, it means meshwork of rods or plates. Trabeculate is rods or plates. And the epiphyses or the cancellous bone has a kind of like a network of trabeculae, means meshwork of rods and plates, meshwork of rods or meshwork of plates. Those are different ways we can connect these rods and plates in the cancellous bone. It has also the spaces, that means the pores, are marrow, they contain marrow. Pores, and the spaces contain marrow. Marrow means the substance, the bone marrow present in the medullary cavity. Medullary cavity, which is also present mainly in the cortex of the bone, again the central part of the bone. So we can have a short revision of this, whatever we have done till now. Macroscopically, seeing the diaphysis or the shaft, it is a really hard structure, but like ivory, but it's very porous. And its strength is at the cortex part. And also one point I forgot to mention is that it is well adapted to many kinds of forces, Well, like tensile force, compression force, bending, twisting, and these are that's the reason I say the main strength is at the cortex, or the central part. Then we move to the epiphyses, or cancellous bone, or trabecular bone. The trabeculae are actually rods or plates whose meshwork forms this cancellous bone. Its meshwork can be in three forms: the meshwork of rods or plates, the meshwork of rods, and the meshwork of plates. Pores in the spaces contain marrow, which is the substance present in the medullary cavity of the bone. And in this pores and spaces also, marrow is present, and it is adapted to compressive forces. Now you may take a look at the board. Moving on to the rest of the video. Let's continue. We stopped at the description of epiphyses and the cancellous bone, of how we see it from naked eye, that means macroscopically. Now we will talk about the Wolff's law and how the bone growth is dependent on the type, the forces that act on it. Bones are actually a marvelous creation. Bones are a marvelous creation because of all the properties in one and in the weight. Actually, it's not that much. If we replace bones with iron, let's say, it will not give the whatever bones give us, because bones have so many properties. They consist of, as I discussed previously in functions, they're lightweight, strong, and the best part of bones, which no other substance, if put in place of bones, can do, is that it can retrieve back. Means if it's broken, it can form again. That's why bones are a marvelous creation, but the growth of bones actually depends on the force and how it develops. The bone development depends on the forces acting over that bone. And also hereditary. How hereditary I'm explaining. Take one generation has brittle bones, or it can also be super strong bones which don't break easily, or brittle bones which break really easily. Then the next few generations will be adapting brittle bones that break very easily. If you hit anything hard, it will break. So brittle bones, that's hereditarily. And also bone development depends on the forces acting on it. Now, the Wolff's law. The trajectory theory of Wolff in 1892. The Wolff's law suggests that The bone development is the rate of growth of the bone. The bone development is directly proportional to the forces acting on the bone. It's same as what I said, depends on it, or it's directly proportional. To the forces acting on it. This is basically the Wolff's law. And also talking about lamellae, which is same as trabecular, as I said previously, the meshwork of rods and plates is also called lamellae. The pressure lamellae are parallel to the lines of the weight transmission on the bone. I'm just writing it here. Pressure lamellae are parallel to lines of weight transmission. And tension lamellae are at right angles to pressure ones. These are all coming from how the bone is treated with the force, of course, pressure. And tension lamellae are at right angles to pressure lamellae. We can have a quick revision. So bones are lightweight, strong, and can form again after breaking or having a fracture. Bone development depends on forces acting on it and also hereditarily. Wolff's law suggests that bone development is directly proportional to the forces acting on it. And lastly, the main point. Pressure lamellae are parallel to lines of weight transmission, and tension lamellae are at right angles. Okay, this looks like 9. Right angles to pressure lamellae. Now you may take a look at the board. Hope you enjoyed this episode, and please like, share, and subscribe my channel, and stay tuned for more videos. Thank you.